Cheers all. Good morning. Let's see. Getting into Desmos. I want to show you something cool there. Morning, Gabriella. How are you? Thanks for showing up with your face on. I feel like I'm not, there's nobody in the room when all I see is names. Let's see. All right, let's play around with something today. Big picture, really, in all of the first four sections of chapter 4, 4.1, 2, 3, and 4. So today is 4.3, tomorrow's 4.4, is really just unmasking the behavior of a graph. So it's good. It's visual. It's not complicated. And it's focused on the same exact idea. And that's what I really want to do, is get into just, I made up some, I don't know, crazy graphs this morning that I want to play with a little bit with you. And so this is kind of cool. I stole this from one of you. I want to say it was somebody in my next class, but this is related to the project. But this is a cubed equation. Maybe you can tell just by looking at it, it's cubed. But I just want you to think for a second about the slope of this graph, because we're actually going to look at a second derivative today for the first time. But I want you to just think about the slope for a second. Down here, I think you'd agree the slope is fairly large, but isn't the slope getting smaller and smaller and smaller as you move along here until actually right there, it actually is 0? And then it actually keeps getting smaller, because now it's actually negative. It's negative tiny, like negative 0.1, negative 0.2, negative 0.3. So it's actually just getting smaller and smaller and smaller, the slope is, as you move along this, until about right here, something interesting happens. And that is the slope starts actually getting larger again. So right here, it might be, say, -1, but then it goes to negative 0.9 and negative 0.5 and negative 0.4. And then finally it's back to 0 again. And then it actually starts increasing back to positive numbers again. Well, watch that happening over here. If I take this point, notice I cheated in here and I said, find G prime of J. And so this is a cubed equation right here. And notice it says the slope down there is actually 3.66. I just want you to watch that happening, watch that slope happening. And I'm going to go back in and just for the visual component to this, even turn the line back on that represents that slope. So remember, that's what we've been doing the entire class. It's like, what's the slope of that curve at a certain point? So if I drag this along, I just want you to watch that number right there. Of course, as I drag this along, it's still positive. It's positive the whole time, but it's getting smaller and smaller and smaller. Now it's still 3, but now it's down into the 2s. And of course, you can see it's on its way up to here, which is 0. The slope is on its way to 0. As you cruise along this graph, the slope is still positive. It's positive, it's positive, it's positive, it's positive. It's positive, it's positive, it's positive. And then finally it's 0. And then it actually just continues to get smaller, but now it actually made it to being negative. In other words, if this is like the value of a stock or something, it was going up. You were really happy down here because the stock was increasing 3.7 points per day. Well, you're still happy here, but now it's only increasing like, 1 point per day. And here you're sort of not super happy because it's leveled off, and you even have this intimation that it actually might be starting to go down. And sure enough, it's negative. Now you're losing 15% per day and losing. But I want you to see how big negative this gets, and watch this carefully. See how it's 0.2, it's negative 0.2, now it's negative 0.22, now it's negative 0.255. It's just getting bigger and bigger negatively. It's getting steeper and steeper and steeper. Now it's up to 0.326 negative. Does it make it to 0.34? Does it make it to 0.35? Yeah, it's up to 0.37, 39, 406, 415, 426. What's the biggest negative it's ever going to get? Like, this is the worst day of your stock, the day you owned your stock. This is the worst.
Probably almost negative 0.5.
Yeah, maybe it makes it to negative 0.5. Notice it is darn close, 496. 496. It's actually kind of hard to move it now. Does it make it to 0.49 to 0.498, 4987, 499? Notice it makes it about to negative 0.5, and it's hard to tell whether it actually makes it to 0.5. Apparently it does. Like right there, it's negative 0.5. But that's a really important point right there. Actually, what we noticed is it was getting worse and worse and worse the whole time. If this is your stock, you're like, hey, it's still positive, but it's not as positive as it used to be. Oh, now it's not growing at all. Oh, now it's actually falling. But at this point right here, it's the steepest negative it's ever going to get. But then notice things start looking up, because now it starts leveling off. Do you see what I'm saying? Like, it was getting 0.4, negative 0.4, negative 0.5. Well, then now it actually starts backing off. Do you see how this is a good sign now? It's like, hey, things are looking up. It's still negative, but it's not growing as fast as it was. And wow, it actually looks like it's on its way to turn around. Now the slope is clear down to negative 0.3, and sure enough, it actually makes it to 0. And of course, that's an exciting day, because it's like, hey, I think I reached the bottom. Like, it's finally bottomed out, and now the slope is beginning to be positive again, and now there's reason for hope. And so, all right, things are going back up again. And so, in a sense, what we're going to study is a little bit more of that behavior. So we said the other day that this was increasing from negative infinity all the way up to 2. It was increasing, meaning it has a positive slope the whole time. And then it's decreasing from x is 2 to x is 14. But notice, as I said, that point right there, somewhere in there, is probably the most interesting, or one of the most interesting points in there, just because it's, well, kind of the halfway point. That happens right at 8. I don't know if I can get it to stop right on that again, but it happens right at, apparently, x is 8. So that's a place where it's negative, the steepest negative, and we're going to find that today with the second derivative. And you might begin thinking about, like, why would a second derivative find that? So it's decreasing the whole time, and then it's increasing again. It's positively sloped from 14 to positive infinity again. And so just want to analyze that. But what I'd like to do now is actually show you something else that's kind of cool. Let me show you what the second derivative is. I think maybe I'll hide the derivative just so you're not looking at it. What's the second derivative? Notice it says g prime prime. And again, I'm cheating in Desmos to get that for free. And incidentally, if you do go to Desmos, that's not g quote. It's not quote. It's prime, like two separate primes, not a quote, even though it looks the same. Notice it's negative right now. Well, what does slope mean? It means change. And so what we're talking about here is, well, the change of the change. Like, how is the change changing? And I alluded to that a second ago, but now we're just like going to put some numbers to it. And so Down here, if this is your stock or the price of your house or something like that, you're pretty happy because it's rising. But what does it mean that the change is negative?
That means that the growth is not growing.
The growth is not growing. The growth is actually negative, which means although the slope right here might be a slope of 6, it's sort of telling us that, hey, the change is negative. The winds are changing, like you're dropping. Like as you move along, if the slope right now is 6 and you move a little to the right, it's going to change from 6, but it's not going to go to 7. It's going to go negatively. It's going to go to 5. You see what I'm saying? A negative second derivative tells you things are actually beginning to level off. It sort of tells us what we see right in front of us here, which is the slope is getting smaller and smaller and smaller. The slope is not getting bigger and bigger and bigger. Would you agree over here the slope is actually getting bigger and bigger and bigger? So what happens if I go over there? Well, what do you notice about the second derivative? It's positive. It's kind of saying like, hey, your slope is actually increasing. Well, kind of think of it as like 39%. So today is good. Tomorrow's even going to be better. What's over here? Today is good. Tomorrow's going to be worse. So if it's positive over here and it's negative over here, then it must go from positive to negative. Let's watch carefully where that happens. Where does that switch from positive to negative go? As I said, your slope here is decreasing, 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 decreasing. And you might have thought when you got here, it'd be 0. But no, that's the slope that's 0. What does that tell you? It just tells you it's still getting worse. Remember over here, you were happy because at least the company was growing, but now you're not so happy because it just continued to drop and now your company is actually losing value. So it's still negative here. It's getting less and less and less. I mean, you think of it as here's a positive slope and here's a negative slope, and that's true, but the slope was getting smaller and smaller and smaller and smaller, and it just continues to get smaller. Now it's even into the negatives. Does that make sense? It's like having a bank account. I had $100 in it, and then I had 80, and then I had 40, and then I had 20, and then I had 0. But now I have -2 and -8 and -20. It just keeps going down, down, down into the negatives.
So when you hit that relative minimum of 14.4, though, that will be 0 because the slope begins to increase at that point, correct?
Conjecture is made by Justin that it's going to get to 0 right here. So watch and see if he's right. Notice that change is really small now. Notice it's still negative, but now it's down to like 0.06. Looks like he's working his way to being right. But actually it zeroed out right there.
Oh yeah, no, that makes perfect sense.
I might have to go in and type it to get this to work, but just so that we don't have to stare at it all this time. Where's my slider? I have a slider in here somewhere for this. There it is. If I get to that same point we were at just a second ago, that's where it's 0. But again, what is this? It's not the slope. It's not telling us the slope. We know the slope is negative there. Remember, the slope was like -0.5. But the change of the slope is 0.
Is that because that's like the halfway point of the graph? I mean, the turning point, like where the graph changes what it's doing?
Yeah. And so this is a really important point, because basically what it's telling us is the whole time it was getting worse and worse and worse. And basically now it's saying, good news today, friends. Today it stops getting worse.
Would that be like 0, 0 if this was just a base equation, like the origin point?
Yeah, could be.
Like with no other extraneous numbers added, if you just graphed like a cubed basic.
Yeah, like a cubed equation might hit 0 right there, but that's random or irrelevant. In other words, this is like year 8 of your stock. It just right there is actually where it's turning. And so does anybody know what that's called? I'm sure your teacher told you this in Math 111, but you might have forgot it. I guess I'm not sure. You may not have. And this is the first time that you really should have been introduced to this. But do you notice over here, does it make sense? The left side of this graph kind of looks like a parabola. It's like concave down. So this word concave needs to mean something to you. So concave down. But then when you look over here, notice it's like concave up. Well, that point right there is the transition between those two. If you look from this point to the left, it kind of looks like a parabola facing down. And then if you look at this point to the right, it's a parabola facing up. That's called an inflection point. I'll write that down in a minute. But that's a change. That's a really important point, because what it means is good news. Your slope is not getting smaller and smaller and smaller. It just double prime equals 0. It just stopped getting smaller, and now it's going to start getting bigger. And notice if I move past that now, for the first time, I have positive changes. And so what does that mean? Even though our slope is negative here, this is saying, yeah, it's negative right now, but good news. Tomorrow, you're going to experience a 2.7% growth. You see what I'm saying? Like, it's getting better, meaning it's going to be less negative in a second than it is right now. Let me pull the derivative back out of here so you can watch that at the same time. The derivative is negative right now. The slope is negative. It's 0.486, but this is telling us good news. In a second, tomorrow, in a minute, this is going to be better than it was. Now, it's still going to be negative, but instead of negative 0.486, maybe it'll only be 0.427. You see what I mean? It's negative, but it's not as negative as it was a second ago. So let's move a little forward. Hey, look at that. See, now it's only 0.465. And your percentage is even getting better. Look, we're going to grow 4% now. It's like things are beginning to look encouraging. Even though they're still on a downturn, there's a hint here that it's turning around. You follow what I'm saying?
See, I was going to say it was an inflection point, but I wasn't sure where that terminology was coming from or whether I was right or not. I was like,
you would have been right. Now, again, notice this point. The slope is 0, but is the change of slope 0? No, because again, we're in a phase where things are really getting better and better and better. Like the inflection, or I'm sorry, the second derivative doesn't find 0 slopes. You need 0 slopes to find 0 slopes. Inflection just tells you about concavity. And basically all through here, things are getting better and better and better. And then they just continue to get better. I just want you to watch how large this begins to get as you kind of move to the right. Whoa, that wasn't good. I grabbed the wrong point, apparently. Wow. Didn't know whatever that was possible. Now I don't know how to undo it.
you just have to set your B point back to where it was.
Oh yeah, I grabbed a B, didn't I? What was it, like 14.4 or something?
Yeah, it's 14.
So that's just kind of cool. I guess since they line up, you got to be kind of careful. So
They became one.
yeah, they became the same point. So you couldn't grab one without grabbing the other. So you see what's happening here? This is saying really good news. Look, you're experiencing 29% growth. So your slope is 1 right now, but your growth is like 29%. So you're really excited now. Not only is the actual rate of change positive, but even the forecast for the future is positive. It's even going to get better and better. So, you know, by the time I get out here, even better. 2.5. Wow, that's really exciting. And 40% growth is projected. I mean, this is really cool. What I want you to notice is just the difference between, see how this is leveling off? That's leveling off over there. It's growing, but it's leveling off. Whereas this is growing and it's just continuing to grow. Like this kind of looks exponential up here. That's exponential growth. It's getting steeper and steeper and steeper. This is positive, but it's getting flatter and flatter and flatter. And so what we're really able to determine is concavity. This over here is concave up, and this from here to here is concave down. And so that inflection point where, and it's very important that you kind of track that. The inflection point is found how? How do you find the inflection point? Come on, let me stop right on it. Let's have a miracle here. I guess I can't.
Is it going to be halfway between the minima and maxima?
The answer is yes. Go ahead, Eldon.
Wouldn't you just set the second derivative to 0 and solve for it?
Yeah, in this case, Justin is right that inflection point is right between 2.8 and 14.4. But that's because this is a cubed equation. It's fairly simple. What Eldon said is safer and works every time, which is notice the second derivative is equal to 0. So if you take two derivatives and then set it equal to 0, then you can find these inflection points. And those are really cool because that's saying, hey, there's a transition from concave down and now it's going to begin to be concave up. And so together, these two things, like can you find 0 slopes and then can you find concavity changes? That allows you to kind of analyze a graph algebraically, if you will. I mean, we have to do calculus to do it, but you can analyze a graph algebraically and kind of know what's happening with it. So again, it just comes down to think caveman before graphing calculators. Somebody's trying to understand what a graph looks like. You got to find a whole bunch of points for a complicated graph. And so we now know 0 slopes, how to find those. Those are really cool points. We call those critical points. But these inflection points are another set of points that are really cool to find. And so armed with really those two things, if you can find inflection points and 0 slopes, like you kind of, those are the best points to find. Like this graph, you could own this graph by just finding 3 points is kind of what it means. Now, what I'm going to give you today is graphs you've never seen before, equations you've never seen. And we're going to find these inflection points and critical points. And then we're going to say, okay, cool. I think I understand what this graph looks like. And in our case, in our generation, it's really cool because then we can go to Desmos and go, hey, sure enough, there's the rest of the graph. And sure enough, it behaved according to those points. And that's kind of what's cool about it. So let's make this a little on the formal side and we will rip into it. And the interesting thing is I don't, in a sense, tomorrow is, I don't know, no different. Like we own graphs now. That's what's kind of exciting about this. Screen is mirroring and we have a note sheet. And I think today, let's choose, I should choose this all the time because graph paper is a cool thing to write on, but let's just write on graph paper instead. So 4.3, I'm just going to call this, what am I going to call this? I guess I'll call it concavity and inflection points. I think your book gives it some name like what derivatives tell us or something like that, which is fine, but this is what it's really about. So let me just make a rough graph, kind of an intro, and just stick a couple of points on it. This is what we just looked at a second ago, but if I had a graph that looked like this and kind of kept on going forever, we said, hey, these points can be easily found by taking the derivative and setting it equal to 0, because those are 0 slopes. F prime of x is equal to 0. Not x is equal to 0. F prime of x is equal to 0. And then what we just learned a second ago is that right in here somewhere is what's called an inflection point. And it can be found by setting the second derivative equal to 0.
See, now I want to know why I know that and where it came from. Because it was in there.
Yeah. Where did you pull that out of? That's exactly right. I was wondering that too. So through this section, we say, what color do I want to use here? Blue. Through this whole section, this thing is concave down. And we saw a second ago that concave down can be determined when f double prime of x is a negative number. That's what we saw a second ago. In other words, things are getting worse. The prediction is your slope is going to get smaller and smaller and smaller. So that's telling us it's concave down. Any point in that yellow area, if you stuck an x value in for that, you'd get something that was concave down. You'd get a negative number. Whereas, if I go over to this wonderful section over here, where we are concave up, this would have a second derivative that is equal to a positive number. Any place in that kind of that green area. But contrast that with this. Would you agree that in this section right here, the first derivative is positive, whereas all through here, the first derivative is negative because it's a negative slope. All through there, you have a negative slope. You're decreasing. So we use the word increasing for when you have a positive slope, and we use the word decreasing when you have a negative slope. And then back out here, the first derivative is back to a positive number again. And so it's actually increasing again. And so by just taking a first and second derivative and playing around with it a little bit, you can kind of own the graph. That's really what this comes down to. So let's play with one now. And this is where the graph paper is going to come in. Let's just play with an example. Let's see how much we can learn about this graph. And none of us have any idea what this looks like. X to the 2/3 times, and I spent some time playing with this to get a graph that kind of has some interesting behavior to it. This graph's got pretty interesting behavior. And of course, I could have distributed that X to the 2/3 inside. And as far as taking a derivative is concerned, that actually might be an easier thing to do. I'm going to go ahead and leave it the way it is to take its derivative. But let's just try to, I mean, ultimately the question is here. And again, put yourself in the cavemen of yore who had like a papyrus with a piece of flint to scratch on it or something of that nature. And they're trying to figure out what a graph like this looks like. And there's never been a substitute for finding a bunch of points, but they didn't even have a calculator to find those points. At least you have a calculator. But we're going to try to figure out what this graph looks like, but we're just going to do it, well, intellectually, or what's the word for that? I'm trying to think of a word here that's analytically is the word I was looking for. We're gonna graph this analytically instead of wimping out with Desmos immediately. And as I said, I admitted to you earlier, this is a bit of an obsolete skill, wouldn't you? Do you? I don't know. What's your thoughts on that? I mean, it's obsolete? Like, do we really need this skill anymore if we have graphing calculators that just present these? I mean, you could say, you certainly should say, well, no, we don't, because we can get the graph in 2 seconds. We don't have to know anything. But I mean, I think there's something to be said, and I'll point this out today. One of the things that's kind of cool about this is it gives you it will find hidden behavior even in a graph that's on Desmos, and that'll happen today. So there's a little bit of value in it.
I was going to say, if you don't understand what's under the hood of how a graphing calculator works, then you're not really going to truly understand how that graph works either,
Yeah. So that's a very debatable point, and I'm never one to try to pretend you need math when you don't need it. I particularly love it when you really do. But do we need this? That's an argument. That's arguable. If you're going to be a teacher someday, you need to think about that a little more. Well, let's go find all of the junk we can find. So what we've learned in 4.1 is that finding the derivative would be really cool. And you should be thinking what when you look at derivative of that junk? What rule? How do I take this derivative? Product. So product rule says derivative of x to the 2/3. Hey, that's just a power rule problem. So the 2/3 comes down front. And then I take 1 away from 2/3, which makes that negative 1/3, times the parabola left alone, plus the x to the 2/3 left alone, times the derivative of the parabola. Again, do you agree with what I said before? Like maybe we should distribute this in there, and then you wouldn't have to do the product rule. There's a pretty good argument for that, perhaps. I just think it looks kind of clean to see it this way. And I'm wondering if it won't simplify. Now, of course, you should look at that and think, oh, Lord, we have to set that equal to 0 and solve it. Like, that's not good. Like, this is crazy. But let me just show you some things some tricks to simplifying things. Because yes, what we need to do now is set that equal to 0 and solve it. But that looks pretty terrifying. And then don't forget, we even have to even go one step further now and now take a second derivative. So, the point is I'd like to clean this up some. And if you got some algebra skills, this will go really easy on you if you do. So let me just point one thing out. It's pretty cool that this term has an x to the negative 1/3 and this has an x to the positive 2/3. And I'll show you why I say that. For instance, I could do something really cool here that would make my life really easy. And this is something I don't think you just kind of would automatically know, but I think it's kind of cool. And I would like you to know it. And so what I'm going to do is take that expression right there, and I'm going to multiply. I'm going to change colors just so this stands out to you. I'm going to take this, treating it like it's a fraction, and I'm going to multiply the top and the bottom by x to the 1/3. Why did I pick x to the 1/3? Why is that really cool? And you should also see that this plus sign is kind of like needs to stand out to you because of distributive law. And let's see. Well, not only that, not only do I not like negative exponents, but I don't like fractions. And so does it make sense to you that I could even do this? I could even multiply it by 3. And because of distributive law, I'm going to add that parenthesis because I basically have to multiply it by this expression and then by that expression there. But I want you to see what this accomplishes. It's kind of cool. So let's see, when I multiply this 3 in here, it cancels with that 3. And then what's x to the 1/3 times x to the negative 1/3? What does that equal?
X to the 0, which is 1, right?
Yeah, x to the 0, which is just 1. And so all I have left then is 2 to get multiplied by x squared plus 3x plus 2. So that gives me 2x squared plus 6x plus 4. So that made my life a lot easier. So there's the first term. What happens when I multiply it by this second term? What happens to the 1/3? When I multiply it by that term.
It just becomes x because it's x to the first, right?
Yeah, isn't x to the 1/3 times x to the 2/3? You add the exponents, just becomes x to the 1. You see, I got rid of the weird exponents. Remember, we got to solve this. And so I don't want weird exponents if I can get rid of them. And so there's a 3 there. There's a 3x. And so what I really have here then is 3x times 2x plus 3. So that's the brilliance of that idea, if you will. So 3x times 2x is 6x squared, and 3x times 3 is 9x. And so that made the top really nice. Now it screwed up the bottom, and notice there wasn't even a denominator here, so that kind of screwed that up. But remember, what's my goal with this? Why am I doing this? I'm not just trying to rewrite the derivative. What am I trying to do?
Set it to 0.
Set it to 0 and solve it. And now I see, hey, that top equation is a squared equation. And man, is that ever nice. Like, that is way nicer than it was before. So that's a cool simplification trick. And so that's my derivative. And so now what is my derivative? I think I can kind of write the simplified version of it. So then it's 2x squared plus 6x squared, which is 8x squared. And then 6x plus 9x is 15x. And then there's a 4 that comes along for the ride. And then there's a 3x to the 1/3 on the bottom, or 3 times the cube root of x. But if I set this equal to 0, again, what makes a fraction equal to 0? Is it the denominator, the numerator, or both?
The numerator.
Yeah, just the numerator. Now, again, you could treat it like an equation. Can't you multiply both sides by 3x to the 1/3 and now you just have 8x squared plus 15x plus 4 equals 0. I mean, you see how much easier that's going to be to solve? So that's a pretty powerful trick. 8x squared plus 15x plus 4 is all that is equal to 0. And so x is approximately, I'm going into my quadratic formula program now, and I'm putting in 8, 15, and 4. And I get negative 0.32. I'll just round it off. And I also get x is approximately negative 1.55. Now, again, what does this tell us about the graph? The fact that I just solved a squared equation that was a derivative and I got two answers. What does this tell us?
It tells you where your critical points are on your graph.
Yeah, and it tells us we have two. It tells us we have maybe, well, it could be a maximum and a minimum like this. Couldn't it be two minimums? It's possible. But it tells us we have two. That's pretty cool. There's only two. Maybe they'll be obvious, maybe not. And of course, it would be nice to cheat because don't I need to go back to this, back to my original graph to find the y coordinate that goes with it? So to save some time, I'm gonna type this equation into my graphing calculator so that I can cheat and get the answers, which of course is kind of a funny thing to do because when I type it into my graphing calculator, I'm gonna get the entire graph. Does that make sense? But I don't want to type all those crazy decimals into that statement right there. And I'm worried that I'm going to do something dumb. It's a waste of time, but I sort of feel like I kind of don't want to see the graph. I'd rather not see the graph at all right now. So for your sake, like, don't do this. Don't look at the graph. I'm just going to tell you the answer to f of x for both of these. So the critical points, and again, I don't like that name because, you have to remember what that means. It really just means zero slopes. So the slope is equal to 0 at negative 0.32. And now I go and put negative 0.32 back into the original equation. I'm not putting it in the slope equation because I know if I put it in the slope equation, I'll get 0. The slope is 0. But I want to put it back into the original graph. And so if I stick in negative 0.32, I get about 0.53. So I'll just make a note here. This would be f of, not f prime, of negative 0.32. That's my y coordinate. And then negative 1.55, same thing. Negative 1.55, I get negative 0.33. And of course, that's f of negative 1.55. And so I have two really important points now to graph. Do you agree with me there? So let's see, if I go make a graph of this, stick this right on. How come you're not making it straight? Oh, well, I guess I'll live with it. Let's see, those are pretty small numbers. I don't know. Made that one straight. So let's see, let's make each one of these. Those are pretty small numbers. So I'm gonna use every other box as being worth 1. So negative 0.32 would be about there, and 0.53 then would be about here. So I've got a 0 slope right there. Now at this point, I don't know, is that concave up or concave down? I don't know that yet. And then negative 1.55 would be about there, and then negative 0.33 would be down. So it'd be about right there. Now I'm kind of thinking, I wish this was even bigger, if you will. I wish I'd made my graph even bigger. Get rid of those little distracting marks. So can you tell what the graph looks like now? I mean, you can probably tell. I'm going to erase this, but doesn't it seem like, do you agree that it's even logically impossible that this is a minimum and this is a maximum? Do you agree that that's not possible? Why is that not possible?
You would need more minimums and maximums to connect them.
Yeah, in order to connect them, you need more minimums and maximums. Now, I guess it could be that this is just a, like a totally separate graph, and this is a totally separate graph. That's not impossible, I guess. That could be the case. But if it's connected, if it's smooth, then wouldn't it have to turn around and go back up and turn around in order to look like that? You see what I'm saying? It creates more. So my guess is I have it wrong. The more kind of logical answer would be that this is a minimum and this is a maximum, right? So maybe something more like that. But again, I don't know that yet. That's kind of the key, is like, I wonder what's going on here. So I'm just thinking out loud a little bit about what it might look like. Well, let's go do the second derivative test now. Let's go see what a second derivative would be. Now remember, I have to take a second derivative of something, and I don't really want to take a second derivative of that statement up there. I'd rather it be as simple as possible. So there's all kinds of algebra I can do to the first derivative before I take a second derivative, and you can make your life easier or hard here, depending on how it goes. And so I'm going to take it of the version I had at least reasonably simplified down. So let's grab this and take it below. I never saw duplicate before. I've done copy and paste. Duplicate. Man, I got to read the directions from time to time.
So what happens if you choose the equation without the denominator to take the derivative of?
Nothing. Same answer. Works great.
So we're just kind of making our life a little bit harder for the sake of learning.
You're saying you think it would be easier to take the derivative of that red one right there. Is that true?
No, the one below, when you multiplied the denominator by 0 and got rid of that ugly denominator. What if you just used that green one right there? You'd get the wrong answer, right?
Yeah, you get the wrong answer, because that was only possible to get rid of because I multiplied both sides by 3x to the 1/3, since this side was equal to 0. So I can't use this red one because it's missing part of what the first derivative was. So I'm glad you asked.
Yeah.
So I have options. I mean, and I honestly don't know. Like I'm staring at this one right now thinking, would that be easier? Part of me looks at it and says, well, it's just product rule again. Maybe that'd be easier. And I really don't know. But I'm looking at this one and I'm thinking, that looks cleaner to me. I don't like the quotient rule, but remember, couldn't you move the x to the 1/3 to the top and have it be x to the negative 1/3? So sure, I'm going to let it sit like it is. But so now let's go find the second derivative. So there's the first derivative. All right, well, then what's the second derivative of x? Well, quotient rule says derivative of the top, which would be 16x plus 15, times the bottom left alone, minus the top left alone, times the derivative of the bottom. What's the derivative of 3x to the 1/3? 1/3 gets multiplied by 3. That's nice. That's just 1. And then I subtract 1 from 1/3. 1/3 minus 1 would be negative 2/3. And then this is all over the top of the bottom squared. I guess I'll just square it now. 3 squared is 9, and x to the 1/3 squared would be x to the 2/3. So again, there's the second derivative. But I'm after inflection points, which is where this is equal to 0. So now, like, again, I don't want to set this equal to 0 now because it's a terrifying looking equation, although I certainly could and begin doing algebra from there. But I'd like to again invite you to think about, what could I multiply the top and the bottom of that by that would get rid of all this nastiness on top? And what I'm looking at is like that and that. I'd really love those to be numbers like 2s or 3s or 1s or 0s or whatever. I want them to be like not so ugly, because I remember I have to set the top of this equal to 0. And so I'd like those to be nicer. What would be a good thing to multiply the top and the bottom of that expression by?
X to the negative 1/3.
X to the negative 1/3. What's your thoughts on that? You agree, disagree?
I was thinking positive 2/3.
Second idea was proposed. Is one of those better than the other?
I guess they would both do the same thing.
So you said x to the first one was x to the 1/3, right?
Yeah, because in the x to the negative 1/3.
X to the negative 1/3. So if that's x
So-
to the negative 1/3, this would become x to the 0.
So that's 3.
This would be x to the 0. This would become x to the negative 1. Do you agree with that? I'd rather not have that be
Just
negative.
moves down to the bottom. Oh, I can't move because, yeah.
I'd rather that not be negative, if possible. Negative 1. Negative 1 is definitely better than what it was. What if I multiplied by, what was the other idea? 2/3? You write that down.
Yeah, positive 2/3.
What happens to this one if I multiply by x to the 2/3? I add exponents, so it becomes x to the 1. So that's just x. What happens to this one?
X to the 0, so it becomes x as well.
X to the 0. So that becomes 1. I like that one better. Like it doesn't have
Or
any
1.
negative numbers. Do you agree with that? Again, stop me regarding, I have to assume you know algebra. I have to assume you can handle exponents, but that doesn't mean you can't stop and say, wait a second, why does that work again? And I'll talk about it. But yeah, they're both good, but this one's better, I guess is what I'm saying. Again, what I'm looking at is this minus sign right here. I'm looking at this minus sign saying I've got to multiply x to the 2/3 times this junk and x to the 2/3 times this. Because this is a multiplication sign right here, I don't have to do this to both of these. Do you understand that? I just pick one. And I'm picking the one that's got the x to the weird expression in it. So I get my 16x plus 15 gets left alone. And my 3 is left alone, but then x to the 2/3 times x to the 1/3 is x to the 1, or just x. And so, hey, that's a nice expression right there. And then minus, and again, my 8x squared plus 15x plus 4 is left alone. But x to the 2/3 times x to the negative 2/3 is x to the 0, which is actually now 1. So I'll go ahead and write that in there. It's actually 1. So that's cool. So do you see how the top is going to be really nice now? And that's what I want. So let's see. And that's all over. Now what happened to the bottom? Is the bottom nice? No, the bottom is not nice. It's x to the 2/3. It's x to the 2/3 times x to the 2/3. I add exponents, so that'd be x to the 4/3. But I don't care if the bottom's weird. That's kind of that's kind of the trick here. So then
Right.
Go ahead.
Because you end up setting it to 0 anyways, right?
Exactly. I'm going to set it equal to 0 anyway. So I kind of only care about the top. So I'm just trying to get the top to be nice. So I multiply 3x times 16x and I get 48x squared, and then 3x times 15, I get 45x. And then the rest of the expression is just what it is. But notice it's minus everything, which means this is minus 8x squared minus 15x minus 4 all over something ugly. And so finally I can say, well, all right, 48x squared minus 8x squared is 40x squared. 45x minus 15x is positive 30x. And then I got a minus 4 that comes along for the ride. And so that's my second derivative. So I just kind of want to highlight that. That's the nicest form. That's the nicest form of my second derivative. As I said, back here in the red, we're done. You've done calculus, you took the second derivative. But if you have to do anything to it, I don't want the red one. I'd like the green one. You see what I'm saying? Take some practice to be good at algebra. So, okay, we got to set that equal to 0. We got to do something with it. I'm just going to go back here and kind of highlight. Seemed like a good idea in the notes that the first and second derivatives would be highlighted. Now I want to set that equal to 0. So all I really have to do then is figure out when is 40x squared plus 30x minus 4 equal to 0. And again, I'm going to cheat and use my quadratic formula program and stick in 40 and 30 and -4. And I might get no answers because there's a negative under the square root sign, meaning there's no inflection points, but I didn't get that. I got 2 inflection points. So at x is approximately 0.12 and x is approximately, being a squared equation, there's 2 answers, -0.6865, so roughly 87, -0.87. So then I got to go back and figure out, now what point is that? Like what, I've got to go find the point on the graph. So I got to put 0.12, notice back, not into this first derivative, not into the second derivative, back in the original equation to see the y that goes with it. So I put 0.2 back in the original equation, 0.12. And when I do that, I get about 0.58 out. And I've got to get -0.87 in for x. When I do that, I get about 0.13 out, both positive. So what this means is I have 2 inflection points. .12, 0.58. And -0.87, 0.13. So again, that's huge. That's, you know, something I need to note. I need to note my 0 slopes, and now I need to note these inflection points. So let's go stick those on the graph. And what I'm saying is, armed with this, we sort of own this graph. We kind of own everything we need to know now. So 0.12, 0.58. So that'd be 0.58 is just a little above. What was that point? The other one, that was 0.53. So this one's a little above that. 0.12, 0.58. It's a little above the black one. And then the other one is -0.87, positive 0.13. -0.87. I think I put this black one in the wrong spot. It was -0.32, which is actually more like here. Since each of my marks is worth a half, you agree with that? So the point I'm trying to graph now is -0.87, 0.13. -0.87, 0.13. So maybe that's like right in here. So here's what I'm thinking now. I'm thinking this graph is concave up to right here. Let me do this in a different color. I'm thinking my graph is concave up to right there. And then here it's a switch to concave down. Do you agree with that? See how it's concave down now? But then what does it mean that that's an inflection point? It means it stops being concave down right there. You see what I'm saying? What would it look like if it's, well, I guess switches to concave up then? What would that have to look like? I want you to think about that. I'm going to label all these really quick. And I'll just round them off so that they're a little smaller. This is 0.12, 0.6. And this other one was negative 0.87, negative 0.9, 0.1. So what does it mean that that's an inflection point? Well, it must switch from concave down. It was concave down through here, then it must actually switch to concave up. So it must look something like that. You see what I'm saying? The question is, if I go to Desmos, is that what I see? Do I indeed own this graph? Maybe I can make use of some of this stuff that's here. So the original graph was x to the 2/3, x raised to the 2/3 times, get out of that, times x squared plus 3x plus 2. Well, hey, that's not what it looks like. Let me stick those points into the graph that I just stuck on there a second ago. While you're staring at it, thinking like, why is that? So that was clearly one of our zero slopes, and the other one was at negative 1.55.
Those scientists with the flint are really pissed right now.
Yeah, they are. Well, the point is there's things to think about. I mean, this is, again, not obvious.
Well, we wouldn't have had enough information to know that, right? We would have had to get like at least one more set of points to the right, because we'd have had a black point on the where it meets at 0, and then a green point up top where it starts shooting up, right?
Yeah, we'll talk about that, and that's why this is kind of cool, because there is something that we missed, and I missed it on purpose in this case. I don't miss it on purpose very often, as you know. But I'll show you how we could have known that. So notice the 2 zero slopes are working. That's working great. And then we had the 2 negatives. So we had the 0.12. So we had that inflection point, and then we had one more, the one that was at negative 0.87. So first of all, would you agree that that all worked? Let me switch the color of this one to purple.
Jason Adams.
This one to blue. So first of all, do you agree? First of all, this inflection point to me is obvious. Do you agree that that really looks like the transition point from concave up to concave down? But had you just looked at the graph over here, would you have noticed over there that there's a transition from concave down to concave up? I can't see that. That's what's kind of cool about calculus, and that's why I made this problem up. And so if you look closer, is it obvious? I don't know. Let me try something here. I don't know. I don't know if I want to do that. Let me look out a little bit. Would you agree that way up here on the right, it's certainly concave up, but then if I look down here at the bottom, it's coming off of 0, 0. Like that's not obvious at all. And so that's actually kind of cool. There's a transition there that I don't know if I could see. Like the math showed it to me, but I don't know if I would have saw it there. But what's with the weird, you know, level off thing? Like stick with that. What's with the fact that it dove down to, you know, something? First of all, it doesn't contradict anything. Would you agree that the slope down there at 0 is not 0? Remember, that was one of those places where graph is not differentiable. And again, I don't, on a test like this is not going to happen on a test. I'm not going to make something up that's this tricky. But how could we have known that? Well, what's the slope down there? Would you agree the slope down there is getting infinitely steep? It's getting really steep, except it's steep negative and it's steep positive. That's why they disagree. But let me take a snapshot of this and let's go back and look at the equation. And I will show you how, in a sense, we could have known that. So what did we learn from this? We just learned, if you will, from the graph that actually it does something more like this. That it really did level off here and it came down to here. I don't know if it looks this way to you, but would you agree my black dot doesn't look like a maximum? I want you to think about something for a second. My black dot was not a maximum the way I drew that a second ago. If it was a maximum, wouldn't it have to go, well, down to be a maximum? But in order to get to that red point, wouldn't it have to turn around and go back up, which means now there's another minimum? So that's kind of my point. Like, we could have actually known something was wrong there. So how can that be a maximum? Well, the reason it can is because it actually went down like this. And then it took off here, and really it went more like that. If I exacerbate the change, that's actually what happened. So let me ask you to stare at something. How could we have known that by looking at this expression right here? I need to put it down here where it's. Let's put it right there. How could we have known that something weird was going on right there from this statement? What happens when you put 0 into this? I didn't say it is 0. I said put 0 in for x. What happens since there's a denominator down here?
It's undefined.
Yeah, it's undefined. Like what? The slope is undefined there? How can a slope be undefined? Remember, undefined doesn't mean you don't know what it is. It means it's infinitely tall. It's infinitely steep. And so that's how this graph got away with going down and not turning around and coming back up again. So again, I'm showing you a much kind of a harder question than I really want you to be able to do here. But you see how calculus is actually helping you figure out the nuance of a graph, how having a slope and having a second derivative, which tells us inflection points, is actually telling you a lot about the graph, and you sort of need to know those to get the hidden nuance of the graph. That's kind of what I'm getting at. So again, my overall goal is to teach you how to think. And I'm going to write here infinity. What undefined really means, it's infinitely steep or infinitely steep, either positive or negative. So that's kind of a trick. Incidentally, 0 slope, the graph can get level for a second and then take off again and still have a 0 slope. That's very possible. And that's what I thought was happening here, in a sense, before I looked at it. So a graph does not have to have a maximum. That's a 0 slope right there. So just be aware of that. So we own the graph, if you will. So let me throw this me throw this in here real quick, the actual graph that's not screwed up. So, and just remind you, that was very hidden. I don't think I would have saw that. I don't think I would have understood what was going on here. And so what we know from this graph now is that here it's concave up and here it's concave up. Because remember, that's what an inflection point means, is the transition. Whereas here and here, it's actually concave down. So it's sort of unfortunate it had that point in it, if you will. Let's try this again. Just a different example. So this is another cool one I made up this morning that is kind of neat. What if f of x is equal to e to the x times, well, a parabola? And you might notice that the parabola creates the interest in this. I mean, if I have a graph like this and it's kind of interesting, I want it to have at least two inflection points or two zero slopes. I want it to have some zero slopes, some hoop-de-doos in it. I mean, it's an interesting graph, and it's actually the parabolic part of this that's actually making that happen. How much time do we have? Man, I want to do this. Oh, we can pick it up tomorrow. I'm also going to add a +3 on the end of this, which lifts it up a little bit. And so let's just go analyze this thing again. Let's go figure out what it looks like. Oh, it's real similar to before, except for the derivative of e to the x is a little different. And so again, let's start out with finding f prime of x. So this is my f prime of x work. So, okay, again, I see this multiplication sign. So I think product rule. So f prime of x, the derivative of e to the x is e to the x times the junk left alone plus the e to the x left alone times the derivative of the parabola, which would be 2x minus 3, and then plus the derivative of 3. Remember, we like plus signs. Plus nothing, so derivative of 3 is nothing. So all that 3 did is move the graph up, and it didn't change the slopes. That's why it has no effect on the slopes. So I got to set this equal to 0. And my process in doing so is going to be greatly increased if I say, hey, look, both of these have an e to the x in it. If I factor in e to the x out of this term and out of this term, then I'm left with x squared minus 3x plus 2 plus 2x minus 3. So my derivative then is equal to e to the x times x squared minus 3x plus 2x, and then plus 2 minus 3. Like that's my first derivative. Junk times junk. So critical points. Critical points happen when that's equal to 0. Remember here, you have junk times junk equals 0. So one answer to this is, when is e to the x equal to 0? Question mark. Do you have the answer to that question? Notice that's weird. Like, when is e to the x equal to 0? The answer is never. Doesn't matter what value you pick for x, you're not going to get that to be equal to 0. So that part of this equation produced none. Play around with that, see that I'm right. Second one is x squared minus x minus 1 equal to 0. And again, that's good to see because it means there's two of them. There's two places here where the slope is equal to 0. And so that'll make a fun graph ultimately. It's going to make kind of a cool graph. So quadratic formula, I put in 1, negative 1, negative 1, 1, negative 1, negative 1. And I get at x is approximately 1.62 and x is approximately negative 0.62. So that's kind of cool. So I'm just quickly sticking this into my calculator so I can evaluate these points. The original graph was x squared minus 3x plus 2. So now I go back and analyze what is the y value that goes with 1.62, and I get the answer to that is, I'm tracing now. This is a much nicer graph. It doesn't have the same weirdness associated with it. So I get 1.81 for that. And when I stick in negative 0.62, I get 5.28. So my zero slopes, or max and minimums, are at 1.62, 1.81, and negative 0.62, 5.28. So this is a big takeaway. This is something I definitely want to highlight. Yes, I found that there are two maximums and minimums. Again, let's stick those on a graph so that we can get our mind around what this thing might look like. See, I got to get 5 to fit on. I'm going to just use the squares like they are. So 1.62, 1.81 would be about there. 1.6 would be about there. Agree with that? And negative 0.62, 1, 2, 3, 4, 5.28 would be about here. Do you agree with that? And again, logically, I'm going to erase this, but I'm thinking, you know, it must do something like this, right? I mean, wouldn't that kind of make sense? It must look like that. And then I don't know what happens after that. Maybe that's the idea. I'm just kind of estimating, guessing, thinking, I don't know. But let's go tackle the second derivative and see if that tells us anything that we might need to know. So we found critical points. Now let's go find inflection points. Again, that means where the second derivative is set equal to 0. Well, I have a first derivative. Let's go steal it. That was a fairly nice form of the first derivative, so let's steal that. You get a step ahead of me. Take the derivative of that. So no different than before. So the second derivative would be product rule again. Derivative of e to the x is e to the x times x squared minus x minus 1 left alone, plus the e to the x left alone times the derivative of x squared minus x minus 1. And like last time, I'm thinking I'll have an easier time setting this equal to 0 if I notice that I can factor the e to the x out from both of them. So now I can say I think the second derivative is equal to e to the x times x squared minus x plus 2x is plus x, and minus 1 is minus 2. So I think that's my second derivative. And if I set that equal to 0, hopefully beautiful things will happen. like last time, the e to the x is not going to contribute any zeros here, or any inflection points. So I'm going to just write a note to myself that e to the x is not equal to 0. That's not possible. But x squared minus plus x squared plus x minus 2 is going to be equal to 0 at x equals quadratic formula, second quit, 1, 1, negative 2. Hey, that's fun. I actually got whole numbered answers. X is 1 and X is negative 2. I didn't have to approximate this time. That's really kind of cool. And so in the interest of time, I'm going to quickly say then that the inflection points are at 1 something and negative 2 something. And what are those somethings?
Mr. Gardner,
Please.
wouldn't it be -1 and then +2? Because if it was -2, then it'd be x squared take away x take away 2.
You're saying you factored it in your mind, and
Am I? I could be wrong. I'm sorry.
I'm glad. I prefer you speak up because it just gives us all time to think. No, I don't think I did anything wrong. In this case, what that tells us is this would have factored, and let's see if it factored, it would have factored to x plus 2, x minus 1. And so, yeah, that's right. It would be negative 2.
Oh, okay. Thank you.
Thanks for speaking up. I'm glad you did. So I just put 1 back into the original equation to find 3. And now if I put negative 2 back into the original equation, I get 4.62. So it's kind of fun that I got a whole number there for a minute, but that didn't last long. So these are my inflection points. And so let's go add those to the graph. 1, 3. 1, 3 is easy to graph. And then negative 2, 4.62. Negative 2, 4.62 be about right there. So what do you think? What's your hypothesis? Why does that first inflection point tell us that this can't be the graph? What's wrong about that? Why can that not be true based on that inflection point? What's an inflection point mean?
Means it changes directions, doesn't it?
Not directions. Well, I think you know, I think you're right. I think you're saying the right thing. It means there's a change of concavity. It means from there to there, this thing is concave down. But does it make sense this can't continue being concave down? It's got to switch to being concave up. So it must look something more like that. Do you see what I'm saying? That's why that's kind of cool, isn't it? And if this one on the right was a switch to being concave up, that would kind of agree. Does it make sense the graph can't look like that? Because wouldn't there be a switch right in here to concave down, and it can't look like that? So that isn't true. What must it be doing over there? It must continue to be concave up. So it must look something like that. Do you see what I'm saying? You see how the inflection points tell us what's happening kind of out beyond what we know?
So how do you know there's not another concave point up in the right somewhere?
I love it. How do we, this is really important. How do we know? Like go graph it and see. Well, how do we know? Well, we know it because the algebra said there was only 2. That's why calculus is cool. The calculus said there was 2 inflection points, not 3. If way out here someplace this kind of turned and went like that, does it make sense that algebra would have told us there's another inflection point up there, and it says there's not?
Do you know how when you're finding the y or x intercepts of parabolas, you can have imaginary numbers? Can you have the same thing with these?
Yeah, maybe you remember from Math 111, like finding x-intercepts. Well, like where does this graph touch? Because it's also nice to know what I'm really trying to say today is ultimately if you only had 4 points that you could find, these are the best 4 you could possibly find. Do you agree with that now? Those are the best possible points you could find. Now, would it also be nice to find x and y intercepts? If there were some, yeah, that'd be kind of cool too. And by the way, notice those x-intercepts are really easy to find. X-intercepts, or I'm sorry, y-intercepts are when x is equal to 0. Like if I went back here and said, when x is equal to 0, what is this all equal to? Well, I have e to the 0, which is 1, and then I just have a 2 left here. And so does it make sense the answer to that is 2? 0, 2 is an easy point to find. Well, wait a second, I forgot about that 3 on the end. Oh, it actually crosses at 5. So it's 1 times 2 plus 3.
I was asking if when you were doing the quadratic formula, it was possible to have a negative
Yeah,
square root. Make it
that's
like
right. What if you had a negative square root? Just because you have a squared equation does not mean you're going to get 2 answers. You might get an imaginary, which means you don't have any inflection points. So that's very possible. I misunderstood your question. So notice, hey, sure enough, that really did cross at 0, 5 in a sense, but that wasn't all that helpful. Do you see what I'm saying? The inflection points told me more. That was a fairly easy point to find. And this is what this graph looks like. Like there's no tricks to this. It definitely looks just like this. So this is what's kind of cool. So I'll highlight one thing and then I got to shut up because it's way over time. But this whole section right here, if you wanted to verify that that was concave down, you could pick any point in there, any point you want. For instance, let's see, where am I? -1, like right here at -1. If I said f double prime of -1, I'm going to get, let's see, it's concave down. I'm going to get a negative answer. I'm going to get a negative answer to that. That would tell me that I'm concave down in between these 2 inflection points right here. I got a negative number, so that means it's concave down. If I chose any point out here, like let's say 3, f double prime of 3 would have been a positive number, which means that section out there is concave up. Negative means concave down. Now, in my case, I was using an educated guess just based on the fact that there's maximums and minimums and inflection points. I was saying this is the only way I think that can happen for sure. But I could have plugged -1 and 3 into my second derivative equation to see if I got a positive or a negative number, and that would have kind of verified, oh yeah, in that section it's concave up or concave down. So the same thing would have happened over here then. If I picked, say, -3, f double prime of -3, I would have gotten a positive answer, which again really tells me, mathematically, it tells me it's concave up out there. So in a sense, you know everything you need to know about graphing. Fortunately, tomorrow we're just going to practice this some more. I mean, it comes up with another title, but really that section is just putting it all together, except for I'm showing you putting it all together today. I didn't feel like you'd understand what a second derivative was really telling you unless we were actually looking at graphs at the same time. So we just need to practice this some more. So I'm going to come up with some more weird graphs for us to play with tomorrow. And maybe ideally these inflection points would tell us some hidden behavior that we didn't know about before. That's kind of the ideal thing that could happen. All right. Sorry I went over yet again. And stay after if you want to ask me questions.
I had a quick question. Do we have class tomorrow? Because it's Veterans Day.
Sorry, I meant Thursday. Yeah, we don't have class tomorrow. We'll